Hello and welcome to today's webinar. We have a very interesting topic today, automated meshing and adaptive remeshing at Bombardier. Before we get started, I want to cover a few administrative details. First, we will be recording today's webinar. Since you're watching live now, if you've registered, you'll be getting an email after the webinar telling you how to access that recorded version. Secondly, we should have some time for questions at the end of the webinar today. If you want to ask a question, we ask that you just type in your question in the GoToWebinar panel, and we'll get to as many of those as we can at the end of the webinar. Also, if you have questions after the webinar, you can see both of our email addresses on this slide, and we'll have the information up on the final slide of the presentation also. So feel free to email either one of us if you think of other things that after the webinar is over and you don't have a chance to ask during the webinar itself. I'm Rick Matus from Pointwise. Our presenter today is Dr. Amine Ben Haj Ali from Bombardier. He's been at Bombardier for about 12 years. He's a senior engineering specialist in their Advanced Aerodynamics group. And he has developed in the last few years an automated meshing system based on Pointwise that automatically generates meshes and also conforms to their company standards, their best practices for meshing. So anyone can generate a high quality mesh very quickly. So very interesting topic. And with that, I'm going to turn things over to Amine.
Okay, good morning everyone, and thank you for joining our webinar today on meshing and adaptive remeshing at Bombardier. My name is Amine Ben Haj Ali. I'm going to discuss how we are using Pointwise as an engine for our meshing system that encapsulates our best practices and produces high-quality grids in a fast, consistent, repeatable, and reliable way. The tool has been developed at Bombardier, so in few words, with nearly 60,000 employees across two business segments, the aviation and train, Bombardier is a global leader in the transportation industry. Bombardier talented engineers are creating innovative and game-changing planes and trains. With three leading aircraft families, the light business jet, the Learjet, the medium business Challenger, and the large luxury business Global, and a diversified train solution, Bombardier offers a product to transport people however they choose to travel. Now, before we get into the details, let's discuss the context, why we need to automate the meshing process. As Rick mentioned, I'm working for the aerodynamics group, and our role is to design aerodynamics configurations and produce aero data. Also, we predict ice and aerothermodynamics. For that, we use one-tunnel testing, flight testing, but of course, more and more CFD, and this is the subject of our discussion today. In terms of CFD package, we use in-house tools and commercial tools. That's why we also develop our CFD capabilities to support aerodynamics and design. So let's move on this slide that summarizes in a very simplistic way two example scenarios where one needs to consider mesh automation. In both situations, we need a CAD, we need to mesh, we need to run our solver, and we need to post-process our results. For the analysis scenario here on the right, you are asked to produce usually aero data on many different configurations at many different conditions. So basically, you are repeating this process for many different times. So clearly, the most important thing is the analysis. You want to deliver the aero data. That's what people are waiting from you. You don't want to spend time meshing thousands of configurations, even though it's fun, but you don't want to miss your delivery. That's why it is very important to automate this part so you can focus on the analysis, on the conclusion. Situation 2 is basically the same thing, but you put the same framework in a loop, and maybe this time you have a parametric CAD that you are perturbating in order to get the best shape that obeys to your function objective. In this case, for the optimization to be practical, you need to automate the whole process, and so you need to automate the meshing part. Now, how at Bombardier we reduced the meshing time, how we automated the meshing process. We've been using pointwise for many years now, and originally we selected pointwise based on many reasons. First, the geometry support. In pointwise, geometry can be imported from a variety of formats. Also, the concept of models and quilts make the mesh topology completely independent from the original geometry topology, while still adhering to the original shape. That's a very good feature in pointwise. Second is quality. Pointwise provide feature and options such as anisotropic cells and mixing usage of structured and unstructured grids that allow us to apply our knowledge and best practices in order to produce quality meshes that satisfies our CFD solver requirements. This is very important in order to get a convergent solution, an accurate solution. I have an example here. This plot shows a CP cut, basically the pressure on a chordwise slice on the wing. Notice the unusual discrepancy between the tunnel results and the CFD results. To make the long story short, the solution was to use pointwise to produce a mesh that we were not able to create with the old tool without exceeding the practical number of elements that our system could afford. The red dots represent the tunnel results. The curve with strange behavior is the solution on the old mesh, a non-pointwise mesh. And finally, the curve that paramatch the tunnel result as the solution with a pointwise mesh. Another reason we selected pointwise is the automatic generation of volume mesh, including the boundary layer, using the famous T-Rex, and the use of multi-block capability that ensure efficiency and consistency. But of course, these qualities, and there are actually more, they come with the price. For complex geometry with a big number of surfaces and curves, making a quality surface mesh could be a tedious and time-consuming process. The good news, pointwise also provide a complete and powerful scripting language called Glyph. Now let's move on to some details on how we mesh using pointwise at Bombardier. This slide you are seeing now summarize the manual process, and you will see later that the automated one is very similar. So without surprise, meshing starts with a CAD. So you need to remove unnecessary feature, closing the gap, avoiding overlap, then maybe checking the axis system and so on till you write a CAD file. The second step is the database preparation. Database is the acronym for geometry in pointwise. After importing the database, we proceed to the model assembly. Then maybe naming and organizing models, and after we proceed to the quilt assembly, and again some organization. At this point, you have a database that is ready to be meshed. We start making the surface mesh by setting our best practices default parameters, then we use the create on database functionality to mesh the models. This produces connectors and domain with isotropic sizes. After that, we start the tedious exercise of adjusting connectors and constraints before we apply surface T-Rex in some area. When the domain are reinitialized, we check the surface mesh quality and we iterate till we are satisfied. Once we are satisfied with the surface mesh, creating the domain, we create the domain boundaries, I mean far field, and if you need a symmetry, and we produce the volume meshing. The volume meshing in pointwise is fairly simple. It's usually you have to set some parameters, and pointwise will do the job. The boundary condition, then we have of course to set the CA solver, the boundary condition, and we export the mesh. Now, if you notice, the steps in orange and red are the ones that are time consuming and painful. So these one that you absolutely want to automate. In the next slide, I will show you how we did this. Okay, here we are. Our automated meshing system using pointwise is called MARS, for Meshing and Adaptive Remeshing Server. Let's start with the big picture. This framework could be considered as an optimization framework or an analysis one, depending if you iterate or you just do one iteration. The general idea is the same, whether they iterate or not so. How MARS is built and how it talk to all these modules. First, MARS is based on pointwise. MARS doesn't replace pointwise. It uses pointwise, and it doesn't replace the user neither. The user uses MARS. As you know, pointwise has an extensive complete API that you can use to call any internal functionality accessible through the user interface, and maybe more. I created a library using object-oriented TCL that mimic all the CLEAF classes, or at least the one of interest for us. On top of the library, I built a plug-and-play system that allows us to augment MARS capabilities with routines to execute small tasks. An example of routines are import, assemble model, assemble quilt, join connectors, export, and so on. And in top of that layer comes another plug-and-play system to add missions. Missions are simple input file with a sequence of tasks and their respective parameters. I will show you an example later. The question now is why it's called meshing and adaptive remeshing server. Meshing is clear. Adaptive remeshing means that it can get some information from your solver on where the mesh need to be refined, and there are mechanisms in MARS to remesh based on these informations. It is called server because MARS can run as a server. That means sitting in the background watching a folder, and every time a user or optimizer place an input file in that folder, MARS will mesh or execute the mission or the list of missions in that input file. So to run MARS, you need a geometry, an input file, and a template. The template is the most important file that you want to protect. It encapsulates all your know-how, best practice, and secret about how you make your meshes. All right, now let's go a little deep in the details. This graphic shows the detailed MARS meshing process. Before getting to MARS, the user need to make sure that the geometry is MARS ready. That means that is idealized, cleaned, and named. We usually prepare the geometry in CATIA, but it is also possible to do so in pointwise. And in the next slide, I will explain why. But for now, let's assume we have a MARS-ready geometry. MARS starts by importing the database. Then based on the instructions from the template, it assembles the models. During the manual process, sometimes you need to adjust the model size and the model tolerance. MARS does that automatically. In the next step, an isotropic coarse mesh is created on models. After, MARS start optimizing the connectors without updating the domains. MARS also adjusts all the constraints and parameters on the fly before any change to the mesh. This is what makes MARS very efficient compared to user, because it's simply impossible for user to optimize thousands of connectors on the fly. We also introduced in MARS some new features. Proximity is a good one. If you look to this mesh, you will notice that you have a very fine connectors in the top here and another coarse one here. Because the difference in the sizing on connector sharing the same domain, and because there is not enough space for the T-Rex to grow, we get that bad quality transition in this area. It is possible in the template to assign the upper connector here as a proximity to the lower connector. By doing that, MARS will split the coarse connector at the closest point and create constraints that ensure a nice transition inside the domain. After adjusting the connector, MARS create T-Rex in the boundary of the domains as per the template instruction, then replace some unstructured mesh domains with structured one. At this point, you get the quality surface mesh. MARS create then a far field and, if needed, a symmetry. It will detect whether the case is a full model, a half model, a 2D mesh, or an extruded 2D mesh, and will create respectively a sphere, a semisphere, a circle, or a cylinder. The last step is fairly simple. Mars create a block, initialize it, and set the solver, set the boundary conditions, and export the mesh. Of course, all this is dictated by the instruction in the template based on the CAD feature name. So talking about name, as I said, we do the naming in CATIA. One, because we create the CAD in CATIA. Also, when the CAD is parametric, it makes sense to do the naming in the very beginning. Two, because we developed this user graphical interface that makes the naming operation very easy and fast. In fact, the user, after selecting the Mars version, only need to select some features like surface and assign them to their respective corresponding name. The GUI has some other options to help the user further find the undefined feature and so on. At Bombardier, this is how we create meshes now. We name our CAD features and we use a template to tell Mars how to make a mesh as per our best practices based on names. Let's practice with a small example to clarify how it works. Imagine this is a geometry that we want to mesh. It is a simplification of a flat track fairing on the wing lower surface. These two surfaces here are the wing lower surface. These two represent the fairing. This one here represents the wing trailing edge, and this one here represents part of the leading edge. I want to create an unstructured mesh, except on the trailing edge, I want it to be structured. I also want to capture the curvature on the leading edge and the trailing edge, and I want to have a fine mesh on the flat track fairing because it's the subject of my analysis. How I will proceed this manually. Okay, so let's mesh. I assume the geometry is Mars 3D. So according to the process we discussed first, the first thing we do is to assemble the model. Since I suppose that we imported an ingest file, usually we get a model and a quilt for each internal surface. So I select all the models and adjust the model tolerance to assign them, to assemble them in one model. So in the end, I got one model, one clean model. Next step is the quilt assembly. So this is where I decide which details in my model I want to keep and which one I don't want the mesh to obey. So my decision is to assemble these two quilts here as a lower surface, as the wing lower surface. I will also assemble these two flap track fairing surface to become one domain, and then I get this clean topology. So the wing lower surface, the trailing edge, the fairing, and the leading edge. The good thing with pointwise is that the mesh will be using this topology. Pointwise will use this topology to make the mesh, but all the mesh point will still obey, or let's say projected on the original geometry, so you don't lose the accuracy. Now, I take the model, I create a mesh using the create on database method. I make a coarse mesh on my model. I get a domain with isotropic cells on each quilt. Next, I refine the fairing. So by selecting all the connectors of the fairing and set their dimension to, by increasing their dimension or changing their average sizing. That will also refine the interior domain depending on your boundary decay. So let's say I do that. Now I said I want to capture the leading edge and the trailing edge curvature. So I will use TRX. This will refine the mesh only on the chordwise direction without adding points in the spinewise direction, which is a very efficient way to refine. Next, I want to make a structured mesh on the trailing edge, and I want to improve the region in front of the fairing. So you see here, like we have that problem of proximity. We have a coarse mesh spanwise here, and you have a very fine mesh on this connector, and there is no enough space for transition, so I need to refine here. To do that, the way I do it, I will split the connectors here, and here, to create a side-by-side pairs with the same dimension and distribution. This also how Mars does it automatically. Okay, by doing that, I'm close to the mesh I want, but as you see, is still some area where I need to improve. And this will take some time because each time you change a constraint or you change the dimension of a connector, you have to work on one side and then you have to work on another side. So you have to iterate like that for some minutes for this simple geometry. Let's say, it took me 10 minutes. After 10 minutes, I get the mesh that I think it's good enough. I got my refinement on the fairing. I got my structured trailing edge. I got my refinement on the leading edge, on the trailing edge. So I'm happy with this mesh, 10 minutes. Now, how we do the same thing with Mars? As I explained, to run Mars, you need three things. You need the Mars-ready geometry, you need a template, and you need a mission. Usually the template is something that you already established. It's something you work on during your day-to-day work. Let's say you have it. The mission is very simple. We said it's a list of sequence of tasks. So usually it will be like import the mesh, read the template, make a coarse mesh, optimize the mesh. So it's a very simple ASCII file that you could write very quickly, but usually you already have a mission too. So what is sometimes missing is the geometry naming, and this operation is very fast using the CATIA GUI. Before I show the resulting mesh, let's open a small discussion on what is automatic and what is automated in Mars. I call automated all the operations that are dictated in the template. The picture on the left is an illustration of our template, how it looks like. It has blocks of instructions, one for the meshing size, one for the mesh type, structured, unstructured, how many points you want, one for applying T-Rex, one for proximity, and so on. There are many other blocks, but I'm showing some of them here for the webinar to be clear. I call automatic all the operations that Mars execute without any information. They are encapsulated, they are hard-coded in Mars. Usually the user have no direct control on this ones, but still he can influence them indirectly by setting the sizes on the quilts. For example, smoothing between domains, setting some sizing at connectors intersection. So like in every intersection, Mars will set the same sizing on all the directions to get a smooth mesh. You don't have what we call a shock in the mesh. As an example, for example, the pylon here, you see that in the corner, in the intersection between the pylon leading edge and the fuselage, Mars refined here, but not in the nacelle leading edge. Like topologically, it's the same thing. You have a domain with a T-Rex, and you have a neighbor domain. You have a domain with a T-Rex, and you have a neighbor domain. Mars refined in this direction here, but it didn't refine in this direction. This is one of the most complex features in Mars, how to detect when to refine and when not to refine. The take-home message is that Mars is a combination of automatic and automated operations, both important for successful balance between speed and flexibility. We want Mars to be fast, but we want to give the flexibility to the user to change whatever feature he wants in his mesh. The mesh should be as his best practices, not as we decided as a programmer. Okay, back to our exercise. This is the mesh generated by Mars. It has all the feature I wanted, and I put in the template. So as you can see in maybe you see it in the statistic table here, it took less than 1 second to import, less than 1 second to assemble the models and quilts, 1 second to read the template, 7 seconds to create the first mesh, the coarse mesh, 4 seconds to create the unstructured trailing edge, 5 seconds to adjust all the connectors, and less than 1 second to export and save the mesh. So overall, 17 seconds. 17 seconds, you get the whole thing done automatically and as your best practice. Now, a qualitative comparison here. The fairing looks better refined with Mars, but overall, the two grids are very similar. Even though I didn't spend enough time to get a perfect match, but in one hand, a power user, an expensive one, 10 minutes. In the other hand, any user, 17 seconds. And this could be someone who has no clue what is pointwise and how to mesh. You just run a command and you get this, this mesh here. This makes Mars essential and for fast turnaround, for quality and for consistency. Even though Mars is considered as a strategic advantage, we believe that successful innovation need collaboration and knowledge sharing. Our participation to the first geometry and mesh generation workshop allowed us to benchmark against other participants. The comparison show how efficient is our meshing system. I remember it took me 15 minutes to make the medium surface mesh. I think some participants didn't believe it at that time. Many precious information from all the participants could be found on the workshop website. We also participated in the second workshop by sending our meshes and data. In the next few slides, I will reuse some slides to show you how fast and consistent is Mars. The test case is a parametric model that we had to mesh at a different parameters, so different shape, different configurations. Every mesh took approximately 15 minutes to be generated from scratch. The number of elements is about 100 million for all of them. They're not exactly the same, but because the configuration is changing, but they're all about 100 million cell. Sorry. Look how is the fuselage changing. And as you can see, the mesh is not changing on the tail, for example. Neither on the wing. So only the fuselage is changing. And by the way, the whole mesh is redone. We remesh from scratch for this exercise. Now another one. In this one, you notice the change in the CAD, but the mesh is still very similar. I'll go more. You see, the wing sweep is changing. The pod is changing. And the last one, the pod is taking a very, let's say, extreme shape, and still the mesh is very, very similar, very consistent. This one, the size is a little higher, 115 million cell, and this is explained because the shape here is very, the diameter of the pod is very small, and in Mars, every component is measured in regarding to its reference length. So if the diameter becomes small, then Mars automatically refine the pod. That's why you get more elements in this case. Now let's move to some Bombardier examples. Since 2017, Mars produced more than 250,000 mesh. 250,000 mesh. It is unfortunate that most of these meshes contain confidential information, so only few of them could serve for this webinar. This one, for example, shows a high lift configuration with a ground effect. So the high lift configuration with the flap deployed, the slats, fairings, all the details here on the slot systems, and also the ground and with the region under the aircraft to refine the mesh under the aircraft. This is based on a parametric CAD. That means we can easily change the flap and the deflection and remesh in a very efficient way. During the webinar, I talked about our template and how Mars understand and mesh about 1,000 of components. This slide shows some of them. So you can see flap track fairings, nacelle, blisters, aileron, pylon, blisters, stall strip, and this one is very difficult one. This is a tricky one to mesh because it has this two connectors going to zero angle there. Mars does that automatically, and you will get I would say a perfect mesh in that corner as per our best practices. Also, we use whatever is provided with pointwise in terms of algorithm. So we use Delaunay, we use Advanced Front Ortho, Voxel. Based on our best practice, we use the respective algorithm when needed. If you remember, Mars is meshing and adaptive remeshing server. This one here illustrates how Mars proceed with the remeshing. The user can define a box in CATIA as a design block. Mars will understand it and will make a mesh with two blocks. A mission called Remesh 3D, delete the design area, import a new design, remesh the surface, recreate the block, initialize the block, and export the whole mesh. A small detail, this can handle boxes that are completely on the wall or partially on the wall, partially in the symmetry. It is a small detail, but very difficult to program. You remember that plug-and-play system? You remember that plug-and-play system? I'm saying like we can plug a mission, we can plug a task. This is a good example how we can use that efficiently. So to make this mission, I had to plug a new task. I think it was for finding some connectors here in the boundary, and I placed a new mission to put a new sequence of tasks in order to get this done. Here are some other examples, multi-block capability usage. In the left, a box that allow the trim of the aircraft. The one in the right is to optimize antennas, shape, and position. Just one note here, the mesh in the left was used for Mars validation and not part of any design or analysis exercise. This is it. It was my last example showing you how we are using pointwise and as an engine for our meshing system that encapsulates our best practices and produces more than 250,000 quality mesh since 2017. Thank you very much for your patience, and please don't hesitate to ask questions. To you, Rick.
Hey, thank you, Amine. That was very nice. So looking at the questions, I see I missed a question at the beginning where somebody asked about audio problems. So I hope that I haven't messed up the audio controls here and that this whole thing was silent. But if you have any other questions, please feel free to type them in, and we'll get to them now as we can. I have a question myself. This system is completely automated. Do you ever take the resulting mesh that comes out of Mars and do any kind of manual manipulation to it in pointwise?
The answer is yes. It was, but it was more often in the beginning when we started using Mars, because we had to work on our template. We had to adjust our template to our best practice. So sometimes we assign something in the template, we think it was the right way, but when we look to the mesh, it doesn't. So usually we don't touch the mesh. Usually we go back to the template, we adjust the template, and we rerun Mars to get the result we like to. But it happens, of course, sometimes when you're getting like 90% of the mesh you want, and you can see visually there is a very small detail, you can fix it quickly. Yeah, sometimes we do that, but it's less and less happening now.
Okay. So do you have people that are using Mars that have never seen pointwise before?
Oh yeah, we have a couple of them. So we have some users that they don't know. Just for fun, like our objective in the beginning, it was to automate some tasks, to automate the one that are really taking time. But with the time, we put an objective for us is not to see pointwise anymore. So it's to create meshes without seeing pointwise, and actually it happens. So we have some users now that are doing an optimization, like a 2D optimization for high lift configuration, or creating meshes, 3D meshes for some configuration without having any expertise with pointwise. Of course, they know how to mesh. I mean, we are in Advanced Aerodynamics, we like skilled people in meshing, but they don't know pointwise. They don't know the details, so they just run Mars. They look to the mesh, they like it. They run their CFD and they're happy.
So maybe I should ask you to put a little reminder whenever Mars runs to let people know that pointwise is there, so they don't forget about us.
They know it. They know it.
Okay. Well,
actually, when you run Mars, you get all the logs with the copyright and everything, saying that this is Mars, that version, using pointwise that version, and so on.
Okay, thanks for that. We don't want to be. We like to be invisible. That's good, but we don't want to be forgotten about. So, thanks for that. So I'm not seeing any other questions here, so I think it's probably okay to wrap things up. Just as a reminder, you can see both of our email addresses there. So if you do think of something that you want to ask later, excuse me, later, or something you just want to get a one-on-one dialogue going with instead of doing it in front of a group, please feel free to email either one of us, particularly anything that Amine talked about today. You can contact him. If you have more general questions just about pointwise or about glyph scripting, you can also contact me. So thank you very much, everyone, for your attention today. I hope that you enjoyed this webinar. I think this is very useful information and a good example of what you can do with pointwise and with glyph scripting. So thank you and have a good day.
Thank you, Rick. Have a nice day, everyone.
Thank you. Bye-bye.